Welcome to the second part of discrete time control. So if you haven't watched, please watch the first version, first video on discretization, and it also provides an introduction to discrete time control. Now I would like to talk about stabilization, one of the main important topics in discrete time control and in control theory in general. Basically, now we have x plus equals to AD, x plus BDU, and y equals to CX. From the we have discretized a continuous time physical system, and we obtain this form. Now we are going to control. So first, let's look at state feedback stabilization, the very basic concept. So control signal that we are going to design in this case is minus k multiplied by x, very similar to the continuous time version, but right now everything is in discrete. I am finding the closed loop system. I am taking this control, injecting to our discretized system. And x here, I am using state x here because state feedback means state vector is available, measurable for feedback purposes. Once you find the closed loop system, we arrive here, AD minus BDK multiplied by x. Now, in this case, we need to ensure that this closed loop system matrix is sure. So sure means slightly different. I will explain what we mean by sure. First of all, when we close the loop and obtain A minus BK with the continuous time system, the resulting closed loop system matrix needs to be Hurwitz. And Hurwitz means all eigenvalues needs to be on the left half plane. Their real parts needs to be negative. In this case, we are going to use the wording sure. And a matrix sure means that all eigenvalues of AD minus BTK needs to stay inside the unit circle. Here's the unit circle on the complex plane. It is basically between minus 1 and 1, j and minus j. It needs to be, all eigenvalues needs to be strictly inside this unit circle. So if all eigenvalues are inside the unit circle, we say that AD minus BTK is sure, and the resulting controller basically will do the stabilization job that I will explain. And you can always find a stabilizing gain matrix K when AD and BD is controllable. Okay, so why inside the unit circle? Let's look at a simple example. Let's say, here AD is n by n, BD is n by m, so K matrix is m by n. So let's look at a scalar case, the super simple one. AD is 0, BD is 1, and control gain is just a scalar gain, K. In this case, the resulting closed loop system x plus becomes 0 minus 1K, right here. So we just have minus kx. So I am going to convert this notation to k plus 1 notation. Remember, x plus represents, it is a just shorthand notation for xk plus 1 and xxk. So in this case, the first computed solution at instant 1 is minus k multiplied by x0. X0 is the initial condition. If you calculate x2, basically if you give k equals to 1, then you have x2 equals to minus kx1. But x1 was this one minus kx0. So if we insert this here, you are going to get k to the power of 2x0. x3 is minus kx2. Why? If we give k equals to 2, you have x3 equals to the next updated x at x3 is minus x2, k is 2, so we obtain x minus kx2. Now if you insert x2, which is here, you obtain x k to the power of 3x0. So this goes like this, iteration goes like this. If k is outside 1 and minus 1 interval, let's say 2, as k goes to infinity, this k to the power of 3, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, your system will diverge and your system will be unstable. if your gain k is like 0.5 inside this unit circle, then you have basically 0.5 to the power of 2 minus 0.5 to the power of 3. Your power of 0.5 will get smaller and smaller, and your x solution will converge to 0, which will achieve stabilization. So this basically, you can generalize this discussion to matrices if your eigenvalues are inside this unit circle, or if you choose the gain matrix K such that the resulting closed-loop system A minus AD minus BDK has eigenvalues inside, strictly inside this unit circle, your solution will converge to 0. Let's look at an example. So you can use pole eigenvalue placement to make AD minus BD, sure. And it works the same way that works for continuous time systems. Basically, you can watch this pole eigenvalue placement. Of course, for continuous time systems, we were interested in making A minus BK Hurwitz, so we are placing poles on the left half plane. In this case, we are going to choose eigenvalues on the unit circle. This is the command. Again, you can learn pole placement by watching this continuous time version. It works the same way for discrete time case. You just need to choose your desired eigenvalues inside the unit circle. This is a sample code. I am having this ADBD. These are the discretized system that I did on the discretization video, previous video on discrete time control, that I use exact discretization, and I mentioned that it is my favorite method. This is the initial conditions. I am choosing using this place command ADBD. I am choosing minus 0.5 and 0.5 and minus 0.5. I am going to talk momentarily, how you should choose eigenvalues to have no oscillations, minimal oscillations, and fast system response for now, and just to random values inside unit circles. And then this is a simulation and plotting purposes. I just posted this code for for you guys. You can basically generate the same result. So you can pause the video, recode this in MATLAB. This is a MATLAB code, and in what follows, I am going to use a bunch of MATLAB examples as well to justify or illustrate theoretical concepts. So as you see, the closed-loop system, x1 goes to 0, sk goes to infinity, x2 and u goes to 0. Here, don't get confused, I am using time because I am plotting them with respect to time. So that's why I have this 0 order halt instead of basically, this is if you remember the first video, I will just show you a time instant for UK. UK was ... like this. Time version is the version that we hold with the 0 order halt operator here, like this, converting this to this. So that's why I have here t, and basically plotting them with respect to time. Anyway, x1 and x2 goes to 0, and this is the control signal. All right, so to use pole placement command or place command, so you need to understand, right? You shouldn't randomly choose eigenvalues, desired eigenvalues inside the unit circle, but there is also meaning of it, like faster response, so on and so forth. I would like to make a resemblance to basically how continuous time control selection, and how you can use your continuous time knowledge to choose, to make you understand how you choose eigenvalues in discrete time. Let's say you are choosing one real eigenvalue. So let's say you have x that equals to minus ax, right? So we know that the eigenvalue of this matrix needs to be located on the left half plane for stability of continuous time systems. So when a equals to 0, x dot equals to 0, right? When a equals to 0, x dot is 0 here. So in this case, motion stops. And we use this basically stopping motion to find the equilibrium points as well. And basically, when a equals to 0, you are here. Your system is stable, or stable in the Lyapunov sense, or marginally stable with respect to the undergraduate terminology. And If you make this A further go to the left half plane, if A is large, then x dot equals to minus A large. So if A is so large, then your x dot immediately goes to 0. So you have a fast response, fast motion. So the point that I'm trying to make is if you choose A, if you start increasing your A 0 to infinity, you will get a faster and faster response. And this is for continuous time systems. Now, you have the discrete time system, x plus equals to a dx. Now, I'm going to use the same A. So like this AD is coming from the exact discretization. You should watch the first video if you have difficulty behind this. This is the exact discretized version of this continuous time system at a given for a given step size delta. So basically, A equals to 0, motion was stopping for the continuous time system. So A equals to 0 means AD equals to e to the power of 0 delta, or 1, right? E to the power of 0. So x plus equals x. Motion stops. So x, the next value of x remains the previous value. So nothing changes. So this is again, so marginal stability in the undergraduate sense, or Lyapunov stability, stability in the sense of Lyapunov. So motion stops in discrete time version as well, meaning that if you choose your eigenvalues at the unit circle in general, or at this -1 and 1 points, your system won't move, motion will stop if you choose AD that comes from this A matrix. So this is basically, I am showing here the I am plotting this with respect to AD, and when A equals to 0, it was corresponding to AD being 1. And when A is large, e to the power of minus A large, right, becomes 0, e to the power of something, minus large. So this Euler number approaches to approximately 0. So as you move here, or with the discrete time analogy, if you approach to the center, you achieve a fast motion. So to wrap up continuous time systems, it was, achieving faster response is for choosing eigenvalues with real parts having large numbers. Here, eigenvalues having real parts close to the origin for discrete time when you choose eigenvalues AD. Let's look at an example. I am using the same example, but instead of using 0.5 and minus 0.5 that we converge around, I would say 6 seconds. Here I am choosing 0.05 and 0.06, smaller numbers close to the origin. You can choose 0 and 0.1. The reason they are different place comment doesn't, in MATLAB, doesn't allow me to choose the same eigenvalues. You can do by hand. So as you see, x1 and x2 converges to 0 way faster, 3 times faster as compared to the previous eigenvalues. Because all eigenvalues that you choose here, you choose 2 eigenvalues because the resulting A minus AD minus BDK system will have 2 by 2 structure. So you need to choose 2 eigenvalues. Sorry if I haven't mentioned this before. So system converges to 0 faster since we choose all eigenvalues small. Now here, if you choose one eigenvalue small and make the other one large, system response will be slow, actually slower than the previous case, because, eigenvalue that is close to the unit circle will be dominating one, is the dominating eigenvalue that will determine the convergence. So if you want to achieve a faster convergence, you cannot leave one eigenvalue large, one slow, one small. You have to choose all eigenvalues here slow to converge to 0 faster. This is for the one eigenvalue. So actually you can look at this nice map that, that we choose eigenvalue with respect to some natural frequency and damping ratio. We know from the continuous time version, right? If your damping ratio is less than 0.707, for the sake of this video, I'm going to use 0.8. So a system will not make, oscillations, maybe a bump, but then it will settle down. So basically, this means that eigenvalues needs to be chosen in this region of the unit circle. This is the unit circle. And of course, natural frequency changes from the application to application, but here I am showing these zeta 0.2, 0.5, 0.8 curves for overshoot. And this is the natural frequency curves. So you need to stay on this yellow highlighted region in order to have basically zeta less than 0.8, which is a good zeta value. It's to be greater than, right? So 0.8, 0.9, if you choose eigenvalues with real parts, zeta will be 1. But to achieve a slightly better rise time, you may want to go for 0.8. So you may want to choose an eigenvalue with some complex parts. For example, if you choose, you may choose here and here. Let's say this is your omega n that you desire, depending on, of course, this changes with respect to given delta. So you can choose two eigenvalues like this. Now, this is for the, not to have oscillations, all right? If you choose an eigenvalue close to 0.5, you are going to see oscillations, which is not desired. So don't choose them as your desired eigenvalues. To summarize, sorry for making it long, to summarize, if you want a smoother system response without oscillations, choose your eigenvalues from this yellow region. And if you want the faster response, stay close to the imaginary axis and choose further your eigenvalues from this blue region. So here, green region. So green region here is the region that you should aim at your faster response without oscillations. I think you got my point. So let's after looking at this, this was for the place command. Basically, if you are using the place command here to choose eigenvalues for AD minus BDK, stay in this region. Alternatively, if you don't want to tweak eigenvalue, if you don't want to tweak eigenvalues. Sorry, I messed up the slides. If you don't want to tweak eigenvalues, but you want to tweak an optimal cost function, you can try optimal linear quadratic control, which in a sense works similar to the continuous time version. Here is the you can review this video for optimal linear quadratic control for continuous time. It works more or less the same for discrete time. Basically, here I am using discrete linear quadratic regulator command. I am entering my AD matrix, BD matrix, and QNR matrices. You need to tweak QNR matrices. For this video, here the same code, I just replaced place with DLQR. Q is I to identity matrix and R is 1. I just wanted to show you this instead of tweaking. If you want me to do a discrete time, LQR video similar to the continuous time example, let me know, we can do. If you use this, it will give you a stabilizing gain that makes AD minus BDK sure matrix. Here in this video, x1 converges to 0, x2 converges to 0, and control signal is like this. All right, so now we know we can make AR, which is AD minus BDK sure. So if the pair AD, BD controllable, so you can always find a gain matrix K using the pole eigenvalue placement, using the place command or the discrete LQR command. Now I would like to make some, I have here one of the most popular videos in my channel, Lyapunov stability and more. Since you can use these Lyapunov stability concepts not only for linear systems, but for time-varying, nonlinear, hybrid, any kind of systems actually. So very powerful method. So I would like to make a comparison, not a comparison, I would like to show you the discrete time version of the classical Lyapunov asymptotic stability of closed-loop systems. Continuous time review, very brief. Basically, continuous time, I am looking at x dot equals to ARX, and we say AR is Hurwitz. right, for asymptotic stability, so that all eigenvalues remain on the left half plane. For discrete time x plus equals to ARx, we need to have AR being sure, all eigenvalues inside unit circle to claim asymptotic stability. We just discussed this. Now I would like to explore this within the context of Lyapunov stability. So if you remember from this video, Lyapunov stability, if you haven't watched, I encourage you to watch. You need a positive definite function and you need its derivative to be negative to claim asymptotic stability. And for linear time invariant systems, you can consider V equals to X transpose Px. P is the solution of the Lyapunov or continuous time Lyapunov equation that we are going to see momentarily. V dot is this. You can stop the video, look at this derivation and leave the comment if you have any comments, but basically I am using this Lyapunov equation for continuous time. And basically for a given R, there always exists a positive definite P if AR is Hurwitz. And basically in the MATLAB, you can use Liap command to directly compute P for a given R. Don't forget to put transpose here, very important. Otherwise, your MATLAB code will create an error. You can see the reason for this. You can write to the MATLAB command window help Liap. So it is for ARP plus PAR transpose, but we need to have transpose here because of this structure. Anyway, so you can directly use this to obtain your P matrix. You can put it here. When you differentiate it, you are going to have minus X transpose Rx. So that you have positive definite V, since P is positive definite and V dot is negative definite. So we have asymptotic stability, actually in this case, exponential stability, right? And discrete time, since we don't have V dot, we still start with the same V equals to X transpose PX, which is positive definite, but we seek delta V. Delta V is V plus minus V. This needs to be less than 0 for asymptotic stability. So I would like to talk about this. Delta V equals to V plus minus V. What is V plus? V plus is X plus transpose P and X plus this minus V itself. Now what is X plus? X plus is ARX. I am just plugging, this to here and here. I obtain this. And you can group the terms like this, X transpose brackets AR transpose P, AR minus P. And if this is minus R, you have, and R being positive definite, you have the difference Lyapunov equation delta V is X minus X transpose Rx less than 0, negative definite. So this brings you to the discrete time Lyapunov equation, 0 equals to AR transpose P AR minus P plus R. So for a given positive definite R, a positive definite P always exists. If AR is sure. So this is a theorem actually I am saying. And if you would like MATLAB to compute your P, you can use the Liap command and don't forget to include transpose here as well. As this being said, let's turn our attention back to feedback stabilization, right? When your system state X is not available for feedback purposes, it is not measurable, so you need to do your design with Y. Quite similar to the actually continuous time, we have this discrete time Lamberger observer. The first part mimics the system, and the system with X replaced with X hat because X is not available. I cannot use it for control. This is my control architecture that I need to implement. And Lamberger gain L, Y, measurable output, minus C, X hat. Basically, in this case, your estimation error, X tilde, X minus X hat, becomes, let's calculate its equation. X tilde plus is X plus minus X hat plus. This is the X plus. This is the minus X hat plus. I just use this and that, nothing else. If you do some arrangement, again, you can stop the video, nothing deep about that, you arrive at this, AD minus LC X tilde. So this is basically the estimation dynamics. So similar to the making, A minus AD minus BDK, sure, if you choose your Lamberger gain L to make AD minus LC sure, then basically estimation error goes to 0, which is good because once your estimation error goes to 0, let's look at x plus. X plus is ADX minus this control signal minus BDKX hat. I am adding and subtracting x. We have AD minus BDKX plus BDK estimation error. If this estimation error goes to 0, once you make AD minus LC sure, then basically x remains, and since this is sure, x goes to 0 as well. You can also observe this from this aggregated system. If you write x plus and x tilde plus dynamics, you have this upper triangular structure, and basically here I am using this equation and this equation together in this cascaded form. You know, this matrix M of the resulting closed-loop system, the eigenvalues of this matrix M, since it has an upper triangular structure, is the spectrum is just a notation to denote eigenvalues of this matrix M, is just the spectrum or eigenvalues of this union the eigenvalues of this. So if you make AD minus LC sure for the estimation dynamics and AD minus BDK sure for the control design, and then x and x tilde together will go to 0. And this is also called the separation principle that I covered. I mentioned about this in the continuous time videos as well. So now how to make AD minus LC sure? Basically, spectrum of this eigenvalues of this AD minus LC matrix equals to the spectrum of its transpose, which is AD transpose C transpose L transpose. If you take the transpose of LC, you obtain C transpose L transpose. Observe that this is kind of looking like A minus B K type of a structure, similar trick to the continuous time case. Since I did these tricks many times in the continuous time state and output feedback control design video, I mentioned, I will probably mention it. I was trying to find what the video name should be called, state and output feedback control. Basically, all you need to do to compute L, if you want to use place command, you use AD transpose CD transpose. The resulting matrix will be n by n. Include your n desired eigenvalues. Don't forget to take transpose. If you would like to use DLQR, use this for dimension appropriate Qn, positive definite QNR matrices. You are going to get your L and D LL matrices using these one of the methods that will make AD minus LC sure. Of course, DLQR will do this automatic. You need to choose eigenvalues here for the place command inside unit circle once again. All right, you survived. This is the final point that I would like to illustrate and output feedback. Then I will conclude the video. Basically, what is different here? Similar to the previous video, we have AD, BD, C output initialization for X, Y. I am choosing K, I am choosing L. So similar to the continuous time case, observation error needs to die out fast, because if this dies out fast, you approximately recover the state feedback stabilization performance. So for this reason, I am choosing desired eigenvalues for the observation error L close to the the origin. X hat is 0, 0 initial condition. Why not, since we don't know X? This is the implementation. You can look at the code, basically plotting for purposes. You can stop the video, copy the code, use for yourself. So here is the output performance going to 0. X tilde estimation error for state 1, dashed line state 2 goes to 0, control signal. And that's it. Okay, thanks for watching this video. And in the next one, we're gonna move from stabilization to command following.